Swayam Prabha. Digital India. Educated India.
Alright. So in this same paper by Michael Jordan, they also introduced something called rescaled gradient flow. Rescaled gradient flows. And as I said, gradient normalization is important. So this rescaled gradient flow was actually scaling the gradient. So the dynamical system looked something like this. So usually for simple gradient flow, we would have x dot is negative of gradient of f. So in rescaled gradient flow, this turns out to be this divided by the norm of the gradient raised to the power p minus 2 over p minus 1 with p greater than equal to strictly greater than 2. Okay. So first of all, is the dynamical system clear to everyone? So this dynamical system has the same equilibrium as the simple gradient flow, right? X equal to x star. I mean, again in this case, in both cases it vanishes at x equal to x star. So it has the same equilibrium as simple gradient flow. Not just that, the trajectory followed by x is exactly the same as the trajectory followed by. So this is just like rescaling the flow, like how quickly you traverse the trajectory, but the trajectory stays the same. So x as a function of time changes, but the phase portrait of x, that remains the same. Okay, so you are just traversing the trajectory much faster than simple gradient flow. It will be exactly the same in continuous time. The moment you discretize, then you cannot say. So in fact, if I just normalize it with respect to the norm of the gradient, that becomes a unit velocity vector field. So that means the velocity changes, but the trajectory that stays the same. Okay. So for this particular rescale gradient flow, so Michael Jordan's group, they showed that the convergence rate is order 1 over t to the p. And if you choose p to be very large, you can practically make it converge much faster, right? So that is the idea. But in order to prove this result, again they use some like the Bregman divergence. So we are going to use Lyapunov theory, and we are going to show something remarkable here. We are in fact going to show that this converges in finite time. The same rescale gradient flow, not just 1 over t to the p. In a finite time capital T, it will converge to the equilibrium. So is the setup clear to everyone? So this is R. So let me denote this by RGF. This p greater than 2 is important, and we will also look at why it is important. But this essentially sort of is a good departure for us to look at something called finite time or fixed time stability. It's Holder continuous at 0. Yeah, I mean as in like at x star essentially. I mean it's Holder continuous, everywhere else it's smooth. It's Holder continuous at x star, but it's not non-smooth per se, it's Holder continuous that way. So usually when you define this kind of dynamical system, you would say that when gradient of f is greater than 0, norm is greater than 0, then you run this, otherwise x dot is equal to 0. So that's how you can typically define, and when in practice when you implement this, you add a small epsilon in the denominator so that there is numerical stability when you implement this in discrete time, but yeah. So this gives rise to two concepts. One is finite time stability and the other is fixed time stability of equilibrium points. So finite time stability, how many of you know Sanjay Bhatt, or heard of Sanjay Bhatt? So he was a faculty here till 2007 in aerospace. He is now at TCS Research, but finite time stability was a seminal contribution during his PhD thesis in 98, I think. So And this fixed time stability is a generalization of finite time stability, and this was proposed by Polyakov very recently, in fact in 2012. And the idea is, with finite time stability, so if I consider the same setup here, so you start in some ball around the let us say equilibrium. So with finite time stability, you are guaranteed to converge to the equilibrium in a finite amount of time t, but this time t is going to be dependent on your initial condition x naught. Okay, so this t is called settling time or settling time function, because it is a function of x naught, right. So settling time function. And t x naught is in fact finite, so strictly. And what do we have? So if origin is the equilibrium, then for every t greater than or equal to t x naught, we have that norm of, or not just norm, xt is equal to 0 for all t greater than this particular time, if origin is the equilibrium. I mean, if x star is the equilibrium, then it would be xt equal to x star for all. So what is fixed time then? So Polyakov generalized this result and showed that with fixed time convergence, so t x naught is independent of x naught. So that means you get initialization independent bound on how quickly you can converge. So let us call this capital T now, because it is independent of x naught initial condition, and Polyakov showed that there exists a fixed time t where independent of the initial condition, for every t greater than or equal to t, xt is equal to 0 for all x naught. So no matter where you start, you are guaranteed to converge to the optimal solution, or in this case the equilibrium, in a fixed amount of time. In the finite time stability case, you are guaranteed to converge again in a finite amount of time, but that amount of time, that time depends on the initial condition. So if you are farther from the equilibrium, you may require larger time to converge, but that is not the case with fixed time stability, where you, even if you are farther away from the equilibrium, you would still converge to the equilibrium in a fixed amount of time. So how does these results first of all have a Lyapunov characterization? So let's look at Lyapunov characterization of finite time stability to get a sense of what this finite time stability is about. So we are now going to look at Lyapunov characterization of finite time stability. So remember, when we had v dot less than or equal to some, let us say v dot is less than or equal to negative v. So we said that v converges exponentially fast, but x, we cannot say anything about x, right. So this talks about exponential convergence of v. So let us look at a different, let us say if I arrive at a different kind of inequality, and I say v dot is less than or equal to v to the alpha, alpha with alpha less than 1. Okay. So let us say we arrive at this kind of inequality on time derivative. Okay. So let us see what does this mean. So that okay. So that's, so what is the integral of this term? 1 over 1 minus alpha, right. Okay. Which basically gives us Vt raised to the 1 minus alpha is less than or equal to V naught 1 minus alpha minus. So V is a Lyapunov function. What do we know about the Lyapunov function? Positive, definite, semi-definite, whatever, but at least we know that this is always greater than or equal to 0, right. So for this to be greater than or equal to 0, this is an increase, like, so this is a constant here. As t keeps on increasing, there would be a point when this term is equal to this term, right. So that means this is the point where your Lyapunov function touches 0, right, because Lyapunov function, yeah, but x is a function of t. So I mean, you can have an explicit function of time, or you need not even have an explicit function of time. The point is that this particular inequality implies that there would be some point after which this right hand side starts becoming negative, right, and because your Lyapunov function cannot be negative, so this is going to be valid only for time t. So this t, let's say this, so there exists some time, let's call this tx naught, which is a finite time such that v naught 1 minus alpha is equal to 1 minus alpha times tx naught, right, or tx naught is equal to, so your x naught kind of shows up in your v naught definition. At the point where you start, you get the initial condition for the Lyapunov function, right, or initial value. So that is why you see the dependence is on the initial condition, but we know that for all t greater than or equal to tx naught, your first of all your Lyapunov function is going to be 0. That means you are going to be at the equilibrium, and you are guaranteed to arrive at the equilibrium in time t less than capital Tx, less than or equal to capital Tx naught. That means you have converged in a finite amount of time if you can show that there exists a Lyapunov function which satisfies this inequality. Okay. So in fact, this is the characterization of fixed time stability of equilibrium, of finite time stability of equilibrium, and so this is the inequality that your Lyapunov function need to satisfy. So your v of x greater than or equal to 0 is strictly greater than 0 when x is not equal to x star, and v dot is less than or equal to negative v raised to the alpha with alpha less than 1. So that is the condition for finite time stability. And not just that, this alpha plays a role. Why? Because you can also characterize the settling time function in terms of this, right. So your settling time function or you can rather say that your settling time is also upper bounded by v naught 1, or let me just write it clearly, v of x naught 1 minus alpha. Okay. So this is true if x star is finite time stable, then this is true, right. Okay. So this basically gives us idea as to, well, the choice of Lyapunov function is fine, but this basically tells us how to design these kind of modified gradient flows. So now let's try to reanalyze this rescaled gradient flow, but instead of using Bregman divergence as was done in the original paper, we will try to use this particular result on finite time stability of a finite time stability, right. So let us do that. No, as long as v is continuous, the settling time, because it's, you get a upper bound directly in terms of v naught, right. So the settling time function is going to be continuous for finite time stability. For fixed time stability anyway, it's independent of the initial condition. So the question of continuity doesn't even show up there. So we have this rescaled gradient flow here, right. Now let's choose the, as I said, like the choice of Lyapunov function, that doesn't change by much. So we assume f is mu strongly convex. Okay. So v I can choose to be half. Okay, that doesn't change by much. That doesn't change at all. So v dot turns out to be gradient f transpose Hessian f times x dot and that's now we are going to be using the RGF or the rescale gradient flow for x dot, right. So, this becomes with p greater than 2. Okay, just from RGF, right, rescale gradient flow. Now, because this is strongly convex, f is strongly convex, Hessian of f is lower bounded by mu times identity. So, I can write this as negative mu divided by the same term okay. Is everyone with me on this? Why? Because since Hessian of f is from a strong convexity and this is basically equal to negative mu gradient of f times 2 minus p minus 2 minus 1, okay, which is equal to negative mu okay, which again I'm not done because I need to write v dot in terms of v, right, less than equal to some v raised to the alpha, and v by definition is this particular thing. So, what I do is minus mu okay, which is minus mu now if p is greater than 2, what is the value of p over 2 times p minus 1? Let us say p is equal to 2.5. So, this term is always less than 1. So, for p greater than 2, by the way, this alpha is not just less than 1, it's also supposed to be greater than 0. Okay. So, which means we have shown that v dot is less than equal to mu and since this term is less than 1, so therefore x star is finite time stable. And what is the settling time function? T of x naught turns out to be v of x naught raised to the power 1 minus alpha, where alpha is, so choose alpha is equal to 1 minus alpha divided by this constant term here, which is mu times 2 to the alpha times 1 minus alpha. Okay, this is your settling time function. So, not only you show that this converges in a finite amount of time, it converges in a finite amount of time, which you can also characterize. So, remember in the earlier case when of exponential stability, we could only say that v converges exponentially fast, but x need not converge exponentially fast. But why can we say, because right now this inequality is in terms of v and not in terms of x, right? Why can we say that x converges in finite time? Because this says that v converges in finite time, right? How can we conclude that x also converges in finite time from here? Yeah, because v is 0 only when x is equal to 0. So, because v has converged in finite time, that means v has converged exactly to 0, v of x star is exactly equal to 0. So, that means x has converged to x star in a finite time, whereas that was not the case earlier. When with exponential stability, I mean we still talk about v converging to 0 exponentially fast, but v can be an arbitrary function of x, right, and that may not converge exponentially fast. In this case, even if it's an arbitrary function, because v of 0 becomes v of t becomes exactly equal to 0. So that means x of t is also exactly equal to 0 or x star. Is this clear? So the same result that that was shown in Jordan's work to be order 1 over t to the p kind of convergence. You in fact using the simple Lyapunov theory, you can get finite time convergence, right? So it's a much bigger result than so in order to show that this converges arbitrarily fast, like using their analysis, you would have to choose p which is very large, right? So that this particular term becomes very small, so you get very fast convergence. But if you use for the same dynamical system, if you use different tools, you can show that it's actually much better. I mean, you can in fact guarantee convergence in a finite amount of time. Okay. So how does this result extend to, how can we generalize this to fixed time stability case? So for finite time stability, we knew that v dot is less than or equal to some c1 v to the alpha 1, where c1 is greater than 0 and alpha 1 is a number between 0 and 1. With this, you can guarantee finite time stability, right, of the equilibrium. If you want to guarantee fixed time stability, you would have to add another term to it with alpha 2 greater than 1 and c2 greater than 0. So if that is the case, then actually you can show that this is fixed time stable. Not just finite time stable, the equilibrium is fixed time stable. So that means no matter where you start, you are guaranteed to converge to the equilibrium in a fixed amount of time. And that settling time function t, it's actually, now it's not a function of x naught, right? It's independent of x naught. That's actually upper bounded by 1 over c1 1 minus alpha 1 plus 1 over c2 alpha 2 minus 1. This is the settling time. Okay. So what is the difference? So how is this particular thing able to guarantee finite time convergence versus why is the other term intuitively, why is the other term able to guarantee fixed time convergence? So let's see what happens when we look at this particular thing, right? So when v is very large, or let's say when v is when norm of v or the value of v is actually less than or equal to 1, by choosing by exponentiating it to alpha, which is a number between 0 and 1, you're making it bigger, right? You're making it bigger. So even when the rate of decrease is actually getting smaller and smaller, you are sort of scaling this up using v raised to the alpha. So the moment you hit that unity ball, v equal to 1, right? After that, you are, unlike the exponential convergence case, you are actually scaling things up, and that is actually leading to faster convergence. But we do not take care of what happens outside that unity ball with this, right? In fact, you are sort of slowing it somewhat. But we still get finite time convergence because we know that the convergence kind of, the convergence is kind of slow only closer to the optimal solution, right? So there you are scaling things up, and that basically helps you with faster convergence, or in this case finite time convergence. In case of this particular condition, you have one term to scale things up when you are inside the unit ball, but because alpha 2 is greater than 1, you actually scale things up when you are outside that unit ball, right? So you converge to the unit ball faster, first of all, and then once you converge to the unit ball, then you converge to the optimal solution or the equilibrium faster because of this term. So these two different terms, they actually have a role at different regimes. So if you start somewhere farther away from the equilibrium, you would have this term basically contributing towards the decrease of the Lyapunov function. The moment you hit the unit ball, this term starts dominating the other term, and that's when you would see that this term would guarantee finite. So you converge to the unit ball in a finite amount of time, once you are in the unit world, you again converge in a finite amount of time. So, in summary, you basically converge in a fixed amount of time independent of the initialization. Now, how does this translate to designing the algorithm? So far, before the rescaled gradient flow, we were analyzing the algorithms that were already known to us, be it gradient flow or Newton's method and things like that, right. Rescaled gradient flow was a way to somehow engineer a different kind of gradient flow that can show faster convergence, right. So, let us look at another rescaled gradient flow or another gradient flow similar to rescaled gradient flow. But this time our objective is to be able to guarantee fixed time convergence, right, and not just finite time. So, as I said, we did not change much in terms of the Lyapunov function, right. Lyapunov function was still the same. So, either you change the algorithm or you change your Lyapunov function so that it satisfies this inequality, right. So, we are going to keep the Lyapunov function as it is, but then we need to be designing our algorithm differently, and now we are going to be using. So, earlier this was the algorithm, okay. Now, I am adding another term to it. Why? Because I want to get that kind of result with my Lyapunov function V. With p greater than 2 and q is a number between 1 and 2. So, without this second term, we had already shown finite time stability or finite time convergence. With this other term, the reason we added this other term is because we want to get this kind of inequality on the Lyapunov function, and with just one term that is not possible, right. So, that also gives you an idea just by looking at what you want to prove or what kind of results or tools that you have. It also gives you an idea as to how you can modify your existing dynamical system, right. And if I really look at this dynamical system from the perspective of gradient normalization, that is nothing but, and you normalize this by p minus 2 or p minus 1 plus. So, this is the normalization factor here in the bracket, and what you are basically running is again a gradient descent, but you are just normalizing the gradient, okay. So, let us see how this guarantees fixed time convergence. So, as I said, we are going to be choosing the same Lyapunov function. Again, we are going to be assuming that f is strongly convex. So, v dot okay, and x dot we are now going to substitute this modified gradient flow. Okay, and this is less than equal to minus mu. If just following the same kind of analysis, it is exactly in fact the same. You get 2v p over 2p minus 1 minus mu 2v q over 2q minus 1, right. That is using the similar analysis that we followed in for finite time stability. That is what we get. So, for the choice of p, so when p is greater than 2, it is basically a number between 0 and 1, and when q is a number between 1 and 2, you can show that, you can clearly see that this particular term is actually a number which is greater than 1. Let us take 1.5. So, yeah, right. So, that means what we get is v dot less than equal to some c1 v raised to the alpha 1 minus c2 v raised to the alpha 2, and that means this x, basically your algorithm is, or your optimal solution is fixed time stable. Equilibrium is fixed time stable. So, your algorithm converges in a fixed amount of time. independent of the initialization, and the settling time t is upper bounded by 1 over this C1 minus alpha 1. Okay. So what did it require us to do? It required us to actually, I mean, we know the result that we want to arrive at, right? And the previous exercise also gave us idea as to what kind of gradient normalization one can potentially use. So if you want to accelerate this further, you can use even better normalization, because we want to arrive at this condition for fixed time stability, right? So you have to add this additional term. Okay. So this kind of gives you an idea as to how one can design new algorithms, right? And this is all motivated from the kind of tools that we have available in continuous time, the kind of stability theory analysis that one can do. And if you have that thing mapped out, then basically it also helps you not just analyze the existing algorithm, but design the new algorithms, right? So you can eventually use this continuous time, implement this in discrete time, and in fact we have done so. While in order to provide guarantee in discrete time is little tricky, empirically it works much better than things like ADAM or RMS-Prof, something that you would have used in for training neural networks. So this is again, like, I mean, it's still a very active field. I mean, in fact, most of this work that you are seeing here in today's lecture, that has been developed in the last 3 to 4 years or 5 years kind of time. So it's a very active research area, but it's a good time to get in this particular field, because I mean, with sort of LLMs and machine learning models becoming larger and larger, you actually have to be able to optimize them much faster, and these kind of tools will actually help you design better and better algorithms. Okay.